Ahora estamos grabando, ya. Lo que vamos a hacer en este momento es presentar a Adolfo.J.Sepúlveda San Martín. Él es una persona destacada que está haciendo un PhD en la Universidad de Laval, supongo, pero que esto es francés, es su université. La área de investigación de Adolfo básicamente es la Biophotonics y laser, y tiene otra área de interacción que a él le interesan. Rodolfo es un ingeniero civil electrónico, titulado en Chile. Bueno, le agradecemos su disposición a colaborar con la gente más joven. Todo este tipo de webinar, etcétera, y lo que nosotros hacemos es, posteriormente se graba, se sube a YouTube, a todas las plataformas que podamos, para llegar a la máxima cantidad de personas. ¿Y lo vas a hacer en inglés o en castellano?
Inglés, para que
Okay,
no
para que entienda la
limitar.
gente. Yeah, so we're just about to start. I would like to welcome Adolfo, and please, Adolfo, please do introduce yourself. I think you are the right person to do it properly. And you can say a couple of words about yourself, and then why you chose this subject to continue with your research activities. So I'm very happy again to have you here, and now
Okay.
can start, my friend.
Okay. Well, first of all, I would like to thank Professor Roberto for this opportunity to present my research work that I'm developing here at Laval University in Quebec, Canada. And today I'm going to talk about one aspect of my PhD project, which is related to the development of a new material, a light-sensitive material, that will be used in microfluidic systems and organ-on-a-chip platforms. So I will give you a brief overview of these two interesting topics. So the title of my talk is Plasmonic-based hybrid nanomaterials towards novel light-driven actuators to control liquid motion at the micro scale. So let me start with the research context of the project. And over the past years, there has been a worrying increase of obesity, cardiometabolic diseases, and mental health disorders among the world population, becoming a major public health issue for every country. And these pathological conditions have come out with and likely as a consequence of many changes in the environment and social and dietary changes over the years. For instance, just as key factors, according to data published by the World Health Organization this year, the worldwide obesity has nearly tripled in the last 50 years, which means that almost 40% of adults over 18 years old are overweight and 13% are obese. These overweight and obesity conditions increase the risk of developing other diseases, including cardiovascular diseases, musculoskeletal disorders, which are degenerative diseases of the joints, and some cancers such as breast, ovarian, and prostate cancers. And linked to this, there's growing evidence showing that changes in the gut microbiome, which is defined as a complex community of microorganisms, bacteria, viruses, and others present in the gastrointestinal tract, may be a common and causal pathogenic mechanism triggering these health conditions. This new scientific understanding not only has caused a revolution in the medical field, as concerns the early identification and treatment of these prevalent diseases, but also has highlighted the lack of predictive tools and biomarkers for rapid and efficient diagnostics. Nowadays, the analysis of the gut microbiota is generally done by employing sequencing techniques on collected stool samples. This approach relies on the extraction of DNA and high-efficiency sequencing technology, which allows identifying and quantifying the phenotypes present in the collective genomes of the environment. The main drawbacks of this method are its complexity, it's highly time-consuming, requires highly trained personnel, and only yields global results with no spatial and poor temporal resolution. So, with the lack of appropriate biomedical tools to study the gut microbiota, many efforts are under development. For instance, our group, in collaborations with others at Université Laval, has been active in developing optical fiber-based probes or lapping fiber systems to measure metabolic markers directly in the gastrointestinal tract of murine models. So, for instance, these are some pictures of the proof of concept fluorescent pH sensitive fiber probe developed in our lab. So here, actually, one of the main challenges is to ensure a continuous flow of fresh solid with the sensing region. So in that case, it's just to avoid moving and bending the fiber when it's implanted in vivo. So in parallel to this effort, recent research has shown how living human intestinal tissue and communities of aerobic and anaerobic human gut microbiota can be co-cultured in a microfluidic device, so-called gut on a chip. So these type of platforms aim to mimic a living human gut that can be submitted, for instance, to variations of effluents, emulating changes in the diet of an individual. However, one of the current limitations in this kind of platforms is the need to overly dilute the microbiome to avoid rapid bacterial overgrowth. So, as a context, my doctoral project is part of Sentinel North, which is a transdisciplinary research initiative of Université Laval, and it aims to contribute to this initiative through the development of novel photonic tools and platforms that will help to identify key biomarkers of cardiometabolic diseases. So to this end, a light-sensitive plasmonic-based hybrid material will be developed to exploit novel light-driven actuators that will be used in both microfluidic and organ-on-a-chip devices. So let me start with some information about microfluidic systems. This type of systems have become very popular in the last decade, I would say, because it has been demonstrated that in a single chip, different reactions, separations, and detections of analytes can be performed, such as a large-scale lab facility, but in a single chip. These systems have been applied in many different areas for chemical, biological, and environmental analysis, as well as in medical diagnosis and therapeutic devices. And the main advantages of using this type of platforms are related to the use of small amounts of reagents, the capacity of parallel operation, and short processing time, as well as their integration capacity with other micro or nano scale technologies, and most importantly, their unique physical and chemical effects at the micro scale. However, the liquid manipulation represents an important aspect in the design of these miniaturized devices. So in this regard, among the major challenges and key factors in microfluidic devices, including lab and organ-on-a-chip platforms, is the transportation and manipulation of small amounts of fluids to perform either reactions analysis or fundamental investigations in many research fields. And the success in such operations requires fine control of fluid motion at the micro scale. Generally, this motion is controlled by means of mechanical, electrokinetic, hydraulic, or pneumatic forces, and usually relies on the implementation of external transducers such as syringe pumps, valves, or electrodes. Even though the viability of these approaches has been demonstrated, the necessity to implement external elements tends to increase the complexity, cost, and the fragility of the devices, and most importantly, limits their miniaturization to be implemented in enclosed spaces. Another crucial and non-trivial parameter to control, particularly in organ-on-a-chip platforms, is the exertion of dynamic mechanical stresses within the culture chambers to accurately simulate physiological environments. Mostly, these mechanical simulations have been achieved using elastic porous membranes that are stretched employing vacuum systems to mimic expansions and contraction movements. However, and despite these approaches have led outstanding improvements in living cell cultures, these mechanical forces are only exerted in 2 dimensions and have lack of temporal and spatial resolution. For instance, the incorporation of peristaltic-like movements within the culture channels of gut-on-a-chip systems is required to control the bacterial overgrowth in communities of gut commensal microbiota, as I mentioned beforehand. So, to overcome some of these limitations, the use of light has become a new paradigm to control liquid motion. This is because the contactless stimulus that light allows, the tunability properties of the wavelength and power excitation, as well as its excellent spatial and temporal resolution. And the major works that have been published in this topic have used 3 main strategies to convert light energy into liquid motion. The first one is related to the transfer of photon momentum by radiation pressure to form an interface, as I show here, or by trapping microparticles with optical tweezers, and that can be used as mobile elements to actuate liquids. For instance, a light-driven pump using optical tweezers applied to microfluidic has been demonstrated like a decade ago, and here a circularly polarized laser beam induced the rotation of microparticles by transferring the spin angular momentum, leading to a maximum flow rate of about 20 picoliter per minute. The other 2 strategies are based on light-induced capillary forces to manipulate fluids. One of them is through the generation of a wettability gradient by partially illuminating a substrate with photosensitive wettability properties. So here we're changing the contact angle between the liquid and the surface, while the other one is through the Marangoni effect, where a gradient of interfacial tension along an interface between 2 fluids generates an interfacial flow along in the direction of the gradient, that is from the lower to the higher interfacial tension. So in this sense, either by optical forces or light-induced capillary forces, light energy has been used to control liquid motion. But in addition to these strategies, advances in polymer science, developing stimulus-responsive polymers, have led the interest of using this type of soft materials as actuators to control liquid motion in microfluidic devices. So just as an example, photoresponsive polymer, BOP, composed of a thermoresponsive polymer functionalized with spiropyrin chromophore, has been used to control liquid motion. So here, blue light irradiation to this material at 420 nanometer induces the polymer shrinks, causing the microvalves to open, as it's shown in these images. Here, what it's important to note is that microvalves open in few seconds, but the main problem is that the closing step requires several minutes or even hours. So in this type of material, or by using chromophores as a light-absorbing means, the main drawback is the low reversibility behavior. So let's imagine having a light-responsive soft material for being used in microfluidic systems, but with reversible behavior, high responsivity, and biocompatible, that could allow to mimic a peristaltic-like motion as occurs in the human gut intestinal tract, where the contraction and relaxation of muscles along the tract allow the fluid to move in specific directions. So what can we find actually in the literature? Well, hydrogels are three-dimensional polymer networks with the capacity to experience important volume changes based on the amount of water stored, which can reach up to 99 weight% of the hydrogel mass. This amount of water defines the swelling and shrunken states of the hydrogels, and depending on the nature of the monomer, these states can be triggered with different external stimuli such as temperature, light, pH, magnetic fields, among others. And what is interesting between the hydrogels are thermoresponsive hydrogels because of their fast dynamic response under a change in temperature. So these thermoresponsive hydrogels can be classified in two types depending on their behavior. Those hydrogels that swell upon heating above a certain critical temperature, they are called, or we say that they have an upper critical solution temperature behavior because it swells, while those ones that shrink upon heating have a lower critical solution temperature behavior. And among the thermoresponsive hydrogels, in the literature we can find that NIPAM is one of the most widely used because of its compatibility with biomedical applications, and in this case, this hydrogel is the type of LCST, and it has a critical temperature of around 32 and 33 Celsius degree. And also what is important here is that we can tune by controlling or by doing the polymerizations with another hydrophilic monomer, we can tune the critical temperature actually. So now that we have this thermoresponsive soft material with a very good reversibility behavior, how can we use light to induce its volume phase transition? So, well, this could be done using metallic plasmonic nanoparticles thanks to their unique electronic and optical properties at the nanoscale. So briefly, when a metallic nanoparticle interacts with an external electric field of a certain frequency, as I show here, the free electrons of the nanoparticle start to collectively oscillate in resonance around the particle with the same electric field frequency. So this oscillation in resonance is known as localized surface plasmon resonance, and at this frequency there is an enhancement of the near electric field. Also, what is interesting about these particles is that they have the ability to absorb and scatter light very efficiently at a specific wavelength, and both absorption and scattering are strongly dependent on the size, type of material, as well as the particle morphology. And also, due to a large optical extension cross-section at visible or near infrared wavelength, plasmonic nanoparticles have a very efficient light-heat conversion. So here, this is the key point in my case to use plasmonic nanoparticles as a heater means to induce the volume phase transition of the NIPAM hydrogel. So taking into consideration what I have shown here, the main goal of my project is to develop a light-activated plasmonic-based hybrid material with reversible behavior and high responsivity to implement it in microfluidic and gas-on-a-chip platforms as light-driven actuators. This includes light-driven peristaltic pumping systems and a light-activated membrane to exploit periodic deformations as those occurring in the human intestine. So for doing that, the first part is to synthesize this hybrid material. And to this, spherical gold nanoparticles can be synthesized by using the one-step Turkevich and seed growth method. So basically, we obtain gold seeds by the reduction of gold chloride, in this case, with sodium citrate as our reducers. And this first step gives us particles of about 15 nanometer in diameter. And after we use these gold nanoparticles as seeds. So by doing a seed growth method, so by applying further growing steps, we can start to increase the particle size. And what is interesting with this technique is that we can easily control the final particle size, depending on the number of growing steps that we have used. So then, once we have these gold nanoparticles of the desired diameter or size, these particles have to be functionalized, in this case with butynylamine, to render the particles hydrophobic. So to allow the precipitation, or the polymerization of the monomer to occur onto the particle's surface. So in this case, well, in my case, I use butynylamine to render the particles hydrophobic. And once these particles are functionalized, I add these particles to the solution containing the monomer and the cross-linker. So this is like a network that I create for the hydrogels. And by using the precipitation polymerization technique, so the monomer, by starting the polymerizations with the initiator, sorry. In this case, I started to create these polymer chains, and they collapse toward the particle surface. So that's a way how we can perform this polymerization and create these gold hydrogel core shell nanoparticles. So now I'm going to show you some results, experimental results about this material. So here, as I showed you beforehand, I start with my gold seeds of about 15 nanometer in diameter, and then by doing further growing steps, I can increase the particle size. So in this case, what I'm showing you here are some transmission electron microscopy images showing that, for example, for the gold seeds, the particle size is about 15 nanometer in diameter, and in this case, after 4 growing steps, the particle size is about 15 nanometers in diameter, and they are quite monodisperse, so it's pretty good. So in terms of the optical properties of these gold nanoparticles, as we can see, well, this is the normalized extinction spectrum for each gold nanoparticles. I didn't mention before, but the extinction spectrum takes into account, or it's the sum between the absorption and the scattering spectra of plasmonic nanoparticles. So here we can see that by increasing the gold particle size, there's a red shift in the plasmon frequency. So, for example, for gold seeds, the plasmon frequency is about 522 nanometers. So at that frequency, the enhancement of the electric field, or it's the maximum, because it's all the electron field electrons are oscillating in resonances. So either the scattering spectrum, or the scattering of light and the absorption of light, it's optimized. It's optimum. And for particles of 50 nanometer in diameter, this frequency is, wavelength is larger, so it goes toward 532 nanometers. And this is because by increasing the particle size, we are changing the polarizability of the particles. So that's the reason why lower energy is required to start to induce these oscillations in resonance. So what about once we have these gold hydrogel core shell nanoparticles? So just as a reminder, we have the gold nanoparticles that we functionalize with the molecule to render the particles hydrophobic. And then we proceed to the precipitation, to the seeded precipitation polymerization synthesis to fabricate these core shell nanoparticles. In terms of the optical properties, here this is the normalized extinction spectra also for of the particles, and for the particles that are coated with the hydrogel shell, there's also a red shift, and this is mainly because we are changing the refractive index of the surrounding medium of the particles. So, because as I mentioned earlier, the plasmon frequency really depends or can be easily tuned either by the particle size, the type of material that we are using, the refractive index of the surrounding medium. So they are very sensitive to this, to the variation of the parameter. So here, for example, I'm showing some results that we're gonna publish in the next days in a journal that we show that actually we can control the encapsulation yield. So this is the number of microgels that we can form and that have having a gold core inside of their network. So actually what we want to show here is that by controlling the number of gold nanoparticles here, or the number of gold nanoparticles that we're adding in the solution to start the polymerization, we can tune the encapsulation yield. So we went from 15% up to 95 or almost 100% of microgels containing a single gold nanoparticle. And so in terms of the optical properties, here we can see that by increasing the number of gold nanoparticles, the plasmonic effect also is most important. So the scattered light and absorption light is more pronounced here. And well, this is normalized to the 400 nanometers, so which is basically like the scatter wavelength for the NIPAM, the hydrogel itself. So, well, as I was mentioning before, what we want to show here is that by controlling the number of nucleation points or gold nanoparticles in the solution that we want to perform the polymerizations, we can easily tune the encapsulations yield of these particles. So here, this is the line. We perform different polymerizations with different particle sizes because in the literature, most of the authors mention that what is important in this type of synthesis is to control the overall surface, in this case gold, the gold surface that is in the solution, in the synthesis itself. But here what we are showing is that no matter what size of particles we are using, but if we control the number of nucleation points, we can tune the encapsulation yield at specific values. So to this, we perform different polymerizations with different particle size by using 50 nanometer gold nanoparticles, 35, 15, and also what we proved that we can also mix this particle size, and we're going to obtain the same encapsulation yield if we control the number of nucleation points. And this is the same, well, these are the same results, but in terms of the overall particle surface. So it's just to prove that for a given, here, for example, for a given number of nucleation points, which leads to a specific encapsulation yield, if we use different particle size, having different overall particle surface in the solution, they have the same encapsulation yield. And this is what's happening actually in these three cases. So, well, this is only just to like how we can control our synthesis protocols, because if we want to apply this material in microfluidic devices or for specific applications, we need to control very well our synthesis. And about the characterization of these materials in terms of their thermoresponsive behavior, I have used the dynamic light scattering technique, which can be used to determine the particle size distribution of small particles in suspension. So here, for example, with this technique, the sample is illuminated with a monochromatic light, such as lasers. So the resulting scatter light or time-dependent scatter light of the particles, because of the Brownian motion of these particles in the solutions, are measured by fast photon detectors. And by analyzing this time-dependent scatter light with a correlator, for example, we can determine the, the particle size or the hydrodynamic diameter of these particles by using the Stokes-Einstein equations. So with this technique, what we are measuring actually is the translational diffusion coefficient, which is related to the velocity of the Brownian motion of particles. And with this equation, where, well, T is the Boltzmann constant, T is the absolute temperature, eta is the viscosity of the medium, and this is the hydrodynamic diameter of the particles. So in principle, the hydrodynamic diameter is defined as the diameter of a sphere that has a specific translational diffusion coefficient. So with this value, actually, what we are obtaining is that, well, we are measuring the Brownian motion velocity, and with this equation, we say, okay, with this value, what should be the particle size or the sphere that has the same translational diffusion coefficient, and then we can do or make the comparison between the two samples. So, for example, to study the thermoresponsive behavior of this material, I perform these DLS measurements, but by measuring the hydrodynamic diameter at different temperatures. So I did two different tests from 15 to 60 Celsius degree and from 60 to 15 to see the reversibility behavior of the hybrid material. And this is the typical hydro or the volume, the particle size transition curve when increasing the temperature. So at temperatures lower of 35 Celsius degree, we see, or we say that the particle it's in, or the particles are in their swollen states, so they are full of water, like as a sponge. And then when we start increasing the temperature, the water starts to be released, and because the polymer is shrinking. And here we can see that actually going from 15 to 60 and from 60 to 15, this behavior is quite tame. And just to confirm that these particles are reversible, I perform some cycles between temperatures from 20 and 50 Celsius degree. And this is what I obtain, that actually I can switch back and forth the swollen and shrunken states of the particles between 20 and 50 Celsius degree in many cycles. And actually the particle size is kept actually pretty constant. So we can see that these particles have a very stable behavior. And also, what happened with the optical properties or with the material when we start increasing or decreasing the temperature? So here, this is scattering the spectrum by exciting these core shell nanoparticles at 400 nanometers, but by increasing the temperature of the surrounding medium. This is by increasing the temperature of the water. So here we can see that by increasing the particles, the scatter intensity, the scattering intensity start to increase. And this is mainly because even if the particles are smaller, the hydrogel network is more dense. So in this case, this more dense sphere will scatter more light as compared what it's in the swollen state, where because of the network, some light can be absorbed. And if we take as a function the peak of the scatter light as a function of the temperature, we obtain a similar curve as I showed you before with the hydrodynamic diameter as a function of the temperature. And here we can see that the critical temperature is about 35 Celsius degree, which is very consistent with what I showed you before. So just to sum up, I would like to say that, well, a new plasmonic-based light-sensitive hybrid material has been developed, and these spherical gold nanoparticles coated with NIPAM have shown a very promising behaviors in terms of their thermoresponsive capability, and also the reversibility that they have. So what I'm working on now is that how we can transfer these hybrid particles that are in solutions, as I show you here in the pictures, how we can transfer this one to a substrate. So just to, in that case, to start developing either the light activated membrane and also the light driven pumping systems. So for that, I have been using, I didn't show anything about the technique, but I'm coating, in this case, it's a microscope slide, the typical one, by deep coating this substrate in the solution containing these particles, and by controlling the speed of the deep coating and also the surface pressure of the particles that are in the interface of water and air, we can easily deposit these particles on the surface. And what is interesting is that these particles actually, they can be arranged in a hexagonally way. So, well, and this type of structures have other very interesting optical properties that we're going to start exploiting in the next month. So just to conclude my presentation, I would like to thank all the members of the research group of my supervisor, Professor Denis Boudreau, as well as the research group of my co-supervisor, Professor André Maret, and of course the funding agencies for supporting my work, especially to Sentinel North for the Sentinel North Doctoral Excellence Scholarship and the SMART program for the complementary scholarship. And of course, thank you for your attentions. And if you have any questions, I'm here to answer. Thank you.
Well, thank you very much, Adolfo. And well, people are more than welcome to ask Adolfo. Please just go ahead. And well, you are quite free to do so. Right. I don't know if Aisha has something to ask. Hello, Aisha. Can you listen me? Right.
It was a very, very nice presentation, Adolfo. I was wanting to ask why you have chosen gold nanoparticles? Why not any other noble metal? Why only gold? What is the special reason for this? Thank you.
Yeah, well, thank you. It's a very good question, actually. Well, mainly because of the wavelength at which we can excite the particles, because we are thinking about for biological applications, we need to be more in the near infrared than in the UV part of the spectrum. And also because of the biocompatibility of gold nanoparticles also with biomedical applications. And the other reason is because gold nanoparticles, they have a very good light to heat transition. Well, they act as a very good heaters in comparison to other noble materials such as silver that we could use. So these are the main reasons why I started to work with gold nanoparticles.
Yes, no, very true. Professor Ambarasan, nice to welcome you here. Do you have something to ask Adolfo? Adolfo is Chilean. A very distinguished experience we have. Please go ahead.
Yes, yes, very nice, interesting talk given by that our
Adolfo.
speaker.
Yes.
Hello.
Yes, his name is
Here,
Adolfo.
hear my voice?
Yes, very well.
Ah, yes. Yes, yes. So in that experimental setup, which kind of laser is used?
Yes.
What is the dosage used for that experimental purpose?
Yes, in this case, most of the GLS experiments uses laser of 633 nanometers. At least, well, that's the wavelength that I was using to do the experiments.
And also in that schematic diagram, I can notice that what kind of lens systems you have arranged.
Yeah, well, that's a good question. I'm not aware about the specific lenses that we were using because this is a commercial instrument. So
yes. Thank you for a nice way of explanation. Thank you, one and all. So thank you very much, Dr. Adolf.
Thank you.
Very nice presentation.
Well, the presentation was very good, actually. And I'm very happy that Adolfo agreed to be with us for a while. And we are going to be in touch. And I hope that Adolfo will agree on that. And I would like to know, Adolfo, which are your plans for the future once you finish your PhD?
Well, that's a tough question, I think. Well, I would like to.
Has never been very simple.
Well, after finishing my PhD, I would like to do a postdoc because I would like to, well, I would like to see if I have the opportunity to work in academia. I really like doing research and also teaching people the things that I'm doing. So that's the main plan.
Right, but do you have some specific place where you would like to go to apply after the PhD? In the first place, well, perhaps the question was put in the wrong order. When do you think you are going to finish your PhD?
Well, I hope to finish it in 2.5 years because it's been, yes, that's the main plan. And after that, I don't really know where I would like to go because my project has two main paths. The first one is developing this type of material, but also how I'm going to apply this material into microfluidic systems. So these are two completely different research areas. But in terms of if I keep working in this type of material, maybe, I don't know yet, I'll go to Germany to do the postdoc because they are quite good in developing this type of materials and the techniques to characterize them. And if I could choose, if I go to the microfluidic part or the development of these platforms, maybe Toronto here in Canada, they are quite good also, or the United States, but I don't really know yet.
Well, yes, because you see now people have to think twice or three times before taking any decision.
Mm-hmm.
Well, there is a world which perhaps you are not very much aware of, but thanks to the Lord, as I said, I know a lot about India nowadays and the quality of the science, which is very, very high. And Professor Ambarasan, the one who asked you, he has a magnificent curricula vitae. And what he's doing a very interesting job. He has in Tamil Nadu a wonderful lab at the physics department. I'm not making a propaganda about him, but he's a brilliant guy, really brilliant. I also know someone who is doing a lot. He's a retired professor. He's a professor of data, and he's really, really, really very, very good. In other words, there are other parts of the world which are doing very good work. I also know Aisha from Pakistan, the lady who asked you.
Okay.
She's doing a beautiful synthetic work, and she's really quite clever. And, I have started to know people that I wish I had known when I was about your age. And, well, it may be because we are so far away from, from country other. Chile is at the very end of the world, roughly. In any case, well, I'm going to give you some information, Adolfo. What do you think about that? Would you like to look at?
Mm-hmm. Yeah, sure.
I will send you some, and I will send you the channel where your this presentation of yours, this webinar is going to be YouTube. I'm going to send you the link. So you will see there all the webinar we have had with very distinguished people and some interviews as well. Well, if there are any question left to be asked to Adolfo, please go ahead. Aisha, would you like to say something?
Yeah, it was very, very nice presentation, very informative, really, for me at least. And I was wondering that what was your inspiration to develop such material?
Sorry,
Why you have chosen this topic for your PhD?
Okay, yeah. Yeah,
I'm sorry. I wanted to ask that what was your inspiration? What was your inspiration to select this topic?
Yeah, it started actually, well, when I arrived here in Canada, because I started my master here. I started to work with the optical fiber probe that I showed you before. I think, what is it? Yeah, this one. So then we started to realize that there's like, it's one of the main problems in this kind, when we want to implement some, I don't know, proof of concept devices or something like this, is that we cannot control like all the parameters. And in this case, for the lapping fiber system, we realized that there was a part missing, which corresponds to the pumping system. So then I started to think, okay, how we can integrate a pumping system at the very nanoscale or microscale, but using light, because we are using optical fibers and light has many advantages, as I mentioned before. So that's the reason why I started to think about on a material that we could use as actuators, actually.
Mhm.
And the reason why, if I go back, because I did my studies in electronic engineering actually, but I also had the opportunity to work in Chile with plasma physics topics, doing research in that. And I, I started to be more interested in doing transdisciplinary research, because sometimes when we focus on a very specific thing or in basic research, sometimes it's not easy to apply this knowledge to a specific problem.
Mhm.
So that's the reason why I decided, okay, I would like to work with bio problems, or how I can use the engineering or the physics applied to this type of biology stuff or platforms. And why I decided to use plasmonic nanoparticles and the hydrogels? Well, because one of the expertise in my research group where I'm working now is plasmonic nanoparticles. And also because they have very interesting features, such as in terms of the light excitation and how we can modulate this excitation. So that is.
Yes.
Thank you. Thank you, Adolfo.
Well, I think, Adolfo, you have been, as usual. I think we came across at the Universidad Mayor. Did we?
Yes. Actually, the first time that I went to the university, I went to ask for the specific program to enter, like scientific talent or something like that. And I had the interview with you when you were
Yeah, because I know your face very well. I said,
yeah.
well, I'm very old, but I can remember faces very, very well. I think you were a student of Enrique Cordaro as well in physics. So,
Yes. And
okay.
also I was his teaching assistant for some courses, physics courses.
Did you have any interaction with Guillermo Cáceres, my dear friend Cáceres, who passed away a
No, I
long
didn't
time
have the
ago?
opportunity to have classes with him.
Yeah. Well, this is a very good example of a young Chilean scientist who is working very hard, and he's doing something very, very, very nice. Well, Adolfo, I would like to congratulate you. I'm going to send you some information, and I will send you the link as soon as it is ready, right?
Okay, thank you so
Thank you very much. I would like to, to send my best wishes and regard to your wife. And you have a very beautiful family. And I think I have seen some picture of your mom as well.
Yes.
And, well, I know your family by Facebook.
Yes.
So my regard and all my love and affection to everybody. You are a beautiful human being, and please do carry on and do work hard and hard. Right?
Yeah.
Okay. I would like to say bye for the time being to everybody. And Adolfo, you want to say something else before we finish this? You're welcome.
Well, I would like to thank you for the invitation. It was a pleasure to me to have the opportunity to present the research work that I'm doing here. And yeah, that is, and of course, thanks to all the people that it's behind me, pushing me to to do this work.
Dear my friend, do take care, be safe and happy, as I say to everybody. And I would like to acknowledge all the people who are in there, who have been listening to Adolfo presentation. And in particular, I would like to thank Professor Ambarasan, H, and everybody. And I think we have had a very good time, and I was quite interested in the job that Adolfo is doing. So thank you very much indeed. And we are going to have another webinar on December the 26th. It's someone from India, a very distinguished friend of mine. And you are going to receive the invitation to join. So thank you very much indeed. And well, the very best of luck for you. And in advance, Merry Christmas and a very Happy New Year, although the difficulty we are going through. Bye-bye. I'm not going to say farewell. I'm just going to say bye-bye and see you soon. It has been lovely to have you. Goodbye.
Bye.
Goodbye.
Bye. Bye, Adolfo. Bye. Bye-bye to everybody.
Thank you.
Thank you, my dear friend. Take care. Bye.
Bye.